So welcome everyone. Thanks very much for joining us for the second day of our annual meeting for the International Environmetric Society. I'm Claire Miller and I'm from the University of Glasgow in Scotland in the UK, and I'm President-elect for the International Environmetric Society. So I'm delighted to welcome you today and also to introduce our first session for today. Our first session is going to be on data fusion for environmental applications. We've got 3 speakers and each speaker will have about 20 minutes, and then hopefully we'll have a few minutes after each presentation for some questions. So first of all, I'm going to pass over to Xiaoyu. Xiaoyu Xiong is our first speaker. So Xiaoyu, do you want to try and share your slides? You're still on mute, Xiaoyu. So our first speaker is Xiaoyu Xiong. Xiaoyu is from the University of Exeter and is going to tell us about data fusion with Gaussian processes for environmental hazard events.
Mute.
That's you, we can hear you now.
All right, sorry. Sorry. Thank you, Claire, very much for inviting me here. So I'm Xiaoyu Xiong. So I'm going to talk about a piece of research I have done, that is data fusion with Gaussian process for estimation of natural hazard events. This is joint work with Dr. Ben Youngman and Professor Theo Economo. So as we all know, environmental hazards such as windstorms or the droughts and the wildfires, which have been a huge problem globally in the last year, can cause severe societal damages. So it is imperative to be able to have a reliable quantification of such environmental hazard events. And the risk is likely to increase with the rapid climate change. So, and the environmental hazard is quantified by the hazard footprint, which is the spatial area describing the potential damage. However, environmental hazards are never directly observed. The estimation of the footprint for any given event is primarily reliant on the station observations. For example, wind gas speed in the case of a windstorm event, and the physical model hindcasts. And we know that both data sources are indirect measurements of the true footprint. And in this work, we have developed a general statistical framework to combine the 2 data sources for estimating the underlying footprint. All right. This picture shows an example of an windstorm event. This shows these observations denoted by the circles, and on the background are these climate model output for the Imogen windstorm over France. So the color indicates intensity of this windstorm event. So as we can see, the station observations lack spatial coverage, but can be sought to measure the true footprint fairly accurately. And the climate model output on the background tends to have complete spatial coverage, but can only model the phenomenon at the model's predetermined resolution and not at smaller scales. And in addition, we can see that the model output tend to exhibit biases compared to the station observations. Sorry. And we know that, however, predictions and the small scales are important due to the large spatial heterogeneity in vulnerability exposure. For example, in the UK, insurers may require accurate estimates of windstorm event for individual postcode regions, which may cover just a few houses. And the prediction at small scale based solely on the observation data is often not accurate due to the sparsity of the station observations. So it's necessary to utilize additional data sources such as model output. However, there are several challenges for integrating multiple data sources for improved spatial interpolation. First, all data sources should be thought of as an imperfect representation of the truth, and the biases can be both systematic and random. And the data sources can have different spatial support. For example, point station measurement and also the graded climate mode output. This is often known as a change of support problem. And also it is very important to accurately quantify uncertainty from all these different sources and propagate this into predictions. And so we have developed a framework that is able to tackle the aforementioned challenges simultaneously. So first we model the true process Z of S. Here S denotes the locations as a Gaussian process with a mean mu and some covariance C Z of S. And we model the observation Y of S as the true process plus some observation error, which is normally distributed with mean 0 and some variance of sigma y squared. And we model the numerical mode of X of S as the function of Z of S plus discrepancy term delta of S. And we model this discrepancy term delta as another Gaussian process to capture the spatially structured discrepancies. So note that both these sources like Y of S and the model output X are conditional upon the true process Z of S. So this model prediction is in principle able to coherently add more data sources. And here is how the change of support is dealt with. This area climate mode up to XAI, where AI denotes a specific area is modeled as integration of this point level numerical climate mode output within that area AI. So by integrating out this true process of ZS, this observational data Y and this the model output X jointly follow another Gaussian multivariate Gaussian distributions with this mean and covariance structure. So it should be noticed that in situations where the number of model output is much larger than this number of observation Y, there might be non-identifiability between these two processes. That is the true Z of S and the discrepancy delta of S. And in practice, this can be avoided by constraining the smoothness of the two processes. For environmental hazard events, we know that the true process is often assumed smoother than the discrepancy term, because the discrepancy term delta S mentioned here, the discrepancy term delta S is effectively an error term, while the true process is a physical process. So in this study, we achieved this by implementing constraint optimization. So this is one note about this framework. So this proposed framework extends the current data fusion framework by allowing structured Gaussian process model discrepancy between the true process and the model output, while retaining the elegance of how the change of support problem is dealt with. And we first did a simulation study to assess the practical feasibility and efficacy of this model framework. So in figure A, we simulate about the true footprint Z of S over a 1 zone by 1 zone grid. So in figure B, we simulate about this area mode up XAI and over a 25 by 25 block. So this figure D shows the simulated data. The black dots indicate the truth ZLS versus our observations YFS, and the blue triangles shows this truth of ZLS versus the area mode output XAI. So it can be seen that by averaging this point level numeric output over an area has induced bias. So this figure C shows this the predictions using our proposed data fusion framework using the simulated data, and it can be seen that the model has captured the truth reasonably well. And we also compare in the simulation study, we also compare these results of the data fusion framework versus the Gaussian model. So for the data framework, we use this both the observation data and the climate model output. And for the Gaussian model, we only using this observational data. And we also tested the impact of the number of these model output on the data fusion framework. And we fixed the number of the observation to be 200. Then we start by randomly sample about 50 area mode output, then increasing at 50 different area mode output until we reach the maximum number of mode output, which is said to be 500 in this study for computational feasibility. And then we compared the root mean square error, the average width of predicted interval, and the coverage probability for these two models over the 30 simulations to represent the 3 different windstorm events. So figure A shows the root mean square result, and B is for the average width predicted interval, and C shows the coverage probability. So in each plot, this dotted line shows the results for the Gaussian model, which is just use the observation data, and the sorting line shows the results for this data fusion model. So as can be seen that by combining this model output with the observations, this data framework can achieve lower root mean square and lower average width predicted interval, but while have very similar coverage probability compared to the Gaussian model, which only use the observation data. And we also applied this model framework to the real data of the windstorm imaging across France. So in figure A, shows the simulated windstorm event from this Met Office unified model output, and they are superimposed by the 128 station observations, which are denoted by circles. So the color indicates the intensities. So it can be seen that there's a discrepancy between these simulated output and the stational observations. In figure B, we plot our model predictions using our data fusion framework by combining the observations and the model output, and also on top of it are the station observations. We can see that the discrepancy between the observations and these predictions is lower at the majority of locations. So this suggests the effectiveness of the data fusion framework for improved spatial interpolation, and it can also work as a way of validating the simulated mode output. And we also validate the model for in this application study. We have used 100 station observations as the training point. We left 28 points as out of sample test point. So this figure A shows these out sample predictions versus other observations. So the sorted line indicates case where the predictions match exactly the observations, and the circles indicate the predicted mean versus observations, and this dotted line indicates the 95 quadrant interval for each outsample test point. So as we can see, out of these 28 test points, only one point is underestimated. So in figure B, we present a spatial map of the standard residuals for these 28 outsample test points. So the one with the largest residual is marked in red. So in this plot, we plot in the figure A, we plotted the 100 observation data we have used in the application. And the figure B, we plotted the 500 meta-office unified model output we used in the model. And this red square is the outsample test point with the largest residuals. So we can see that these test points, the values of this test point is much higher than the observations and also the model bout in the nearby area. So this suggests this data flow theory can be used to highlight outliers, for example, potentially erroneous observations. But it also indicates that future work could improve on the model's capability to capture the extreme values. So there are some limitations for this framework as well. First, we have only used isotropic radial-based function covariance for the Gaussian process model. This implies that the sample paths of the GPs are indefinitely differentiable, and this might not be a proper assumption for some processes, such as the high-resolution rainfall measurements derived from reader data, which tend to have much greater short-scale variability. And so we could explore some power exponential or the maternal covariance for such process. And also second, that this model framework implies a Gaussian marginal distribution for the wind gust speed. So while our study supports this to be a reasonable model for gust speed within a single windstorm event, we could investigate a more flexible marginal model, such as transferred Gaussian process, where a box cost transformation of the response is performed to for other processes. And also in the application, we only subsampled 500 this climate mode output out of its available around 30,000 climate output for computational feasibility of the Gaussian process models. So another direction would be exploit the sparse GPs to incorporate all the data points for a more accurate and reliable estimate. And as I mentioned earlier, this model framework is in principle able to generalize to other data sources. So we could extend this framework to incorporate more than 2 data sources. So thank you very much.
Thank you very much, Xiaoyu, for a really interesting presentation. So we've got a few minutes now for questions, and so you can feel free either to raise your hand or to put any questions that you have in the chat. While we're giving everyone a minute to think, Xiaoyu, I was actually just going to follow up on the very last point that you made, because I was wondering about incorporating additional data sources. So, of course, at the moment, very often you might have more than just the in situ in the model. You might be in the case where you might have drone output or something as well. So do you have a feeling just now as to how you would extend your framework for multiple data sources beyond 2?
Yes, actually, as I mentioned in the slides as well, because in these 2 data example, these 2 data sources are conditional on the truth process, right? So we could just add another data sources or even models that also conditional on the truth with a different maybe a bias term.
Okay. Yeah. And you mentioned about using a sparse GP potentially as well, so that you could scale up the computation. what kind of computational times are you working on at the moment for what you're currently using?
Oh, for the one I just used, because because we know the GP suffers these scaling problems. So in this application, we only use about 500 models plus 100 observations. So that's the 600. So, but actually we have about 30,000. So it could be a very dense matrix. So if we can exploit the sparsity of this matrix, we could use more data point. That could be actually.
Thank you, Xiaoyu. We've got time for another question. Abdul, I think you have your hand raised.
Yes, I did. I just would like to go back to the original model that you have given. And I was quite surprised about the variance-covariance matrix that you have included in your bivariate Gaussian model. It seems to me that it is function of the observations or how you are generating the sum xy, the sum x square, the sum whatever it is. All this matrix seems to be well defined. This means that you generated the x and the y, or what? How did you do this?
Sorry, I think the voice is not very clear due to the internet. Would you please put it in the chat as well? So very sorry about that.
Thank you to you both. We should maybe move on, Abdul. So if you didn't mind typing your question in the chat, that would be really helpful.
I think it's okay. I'll send it to her. But okay, it's okay. Thank you.
Great. Thank you so much. Thank you. Thanks very much again, Xiaoyu, for your presentation. And we'll move on now to our next speaker today.
Thank you.
So